Today we will be discussing orthonormal basis and Gram-Schmidt orthogonalization procedure. We will begin with definitions. So first, let V be either a Euclidean space Rn or a Hermitian space Cn with the Hermitian scalar product. So we define a basis V1 through Vn of V is called orthogonal if for all I different from j from 1 to n, the scalar product of Vi with Vj is equal to 0. A basis V1 through Vn of V is called orthonormal if it is orthogonal and in addition to this, for all k from 1 to n, the scalar product of Vk with itself is equal to 1. Let us mention that this terminology is not quite standard. So in the literature, the term orthogonal basis usually stands for what we call the orthonormal basis. But I find it useful to distinguish between these two concepts. Of course, if we have an orthogonal basis, it is very easy to obtain an orthonormal basis from it. So this is done through normalization procedure. So let V1 through Vn be an orthogonal basis. And set vectors uk to be 1 over length of vk times vk for k from 1 to n. So we divide each vector by its length. Then the new set u1 through un is an orthonormal basis. So when we divide a vector by its length, we obtain a vector of length 1. And so it's very easy to check that the basis of UKs will still be orthogonal, but in addition, each vector will have length 1, so the new basis is orthonormal. Let us see what's the advantage in using orthonormal basis. Proposition. Let u1 through un be an orthonormal basis of V, And let V be a vector in our vector space. Suppose we want to expand this vector V as a linear combination of the basis vectors. So C1 U1 plus C2 U2 plus Cn Un. Then the coefficients of this expansion can be computed using the scalar product. So this will be the scalar product of vectors uk with v, for k goes from 1 to n. For the proof, so we know that since we have a basis, such an expansion exists. So we are going to take this expansion. V is C1 U1 plus C2 U2 plus Cn Un, and then compute the scalar product of arbitrary vector uk with v. Then we get that uk with v, so for v we substitute this linear combination, so this is equal to uk with c1 u1 plus ck uk plus cn un. And then, because the Hermitian scalar product is linear in the second argument, so this is equal to C1 scalar product of UK with U1 plus CK scalar product of UK with UK plus Cn scalar product of UK with UN. But our basis is orthonormal. So the scalar product of UK with U1 is equal to 0. And all scalar products except UK with UK all vanish. And UK with UK scalar product is equal to 1 because we have an orthonormal basis. And what we see is that this scalar product of V with kth basis vector is equal to CK. And this allows us to determine the coefficient CK. What happens if our basis is just orthogonal and not orthonormal? So here we make a remark, which I leave it for you as an exercise. So let W1 through Wn be an orthogonal basis of V. And let V be a vector in this vector space. And we want to expand this vector V as a linear combination C1W1 plus CNWN. Then the coefficient CK can be calculated as the scalar product of WK with V divided by scalar product of WK with itself for K from 1 to n. For orthonormal basis, of course, all denominators will be equal to 1, and we obtain our previous formulas. Let us see why this method gives us computational advantages. Suppose basis U1 through UN is not orthogonal. And we need to find an expansion of a given vector V as a linear combination, C1 U1 plus Cn Un. So how do we do this? So this becomes a vector equation. And when we write our basis vectors as columns, So this becomes a system of linear equations with n equations and n unknowns. To solve this system, we run Gaussian elimination, and the computational complexity of Gaussian elimination algorithm is O of n cubed. This means that the number of multiplications or the number of additions is a polynomial in n of degree 3. Let us see why this is true. So how do we run the Gaussian elimination algorithm? We take one pivot and then create a column of zeros below it. For one pivot, this requires n elementary row operations. Next, we need to repeat this for n pivots. So the number of elementary row operations of type 1 now becomes n squared, or perhaps n squared over 2. But then we also need to create zeros above the pivots. And now the number of elementary row operations of type 1 becomes a quadratic polynomial in n. When we consider floating point operations with multiplications and additions, then we know that multiplications are more expensive. So typically it takes 10 times longer to perform one multiplication on a computer than one floating point addition. And so it makes sense to count the number of multiplications. However, in this case, the number of additions will be very similar. When we perform one elementary row operation of type 1, we need n multiplications. And given that the number of elementary row operations of type 1 in Gaussian elimination is a quadratic polynomial in n, then the number of multiplications becomes the cubic polynomial in n. And we say that the computational complexity of Gaussian elimination is big O of n cubed. This means that the number of multiplications that we need to perform is a cubic polynomial in n. Now, if our basis u1 through un is orthonormal, then we compute our coefficient ck as scalar products of uk with v. And computing the scalar product of two n-component vectors requires n multiplications. So since we have n coefficients to compute, then computational complexity is n times n, so this becomes n squared. Now, for large n, n squared is much better than n cubed. If n is equal to 1000, then for orthonormal basis, we need to perform 1,000,000 multiplications. And for non-orthonormal basis, to find the coefficients of this linear expansion, we need to perform billions of multiplications. Thus, clearly, working with orthonormal basis will give us computational advantages. In modern applications of linear algebra, such as statistics, data science, or digital signal processing, we work with data in very high dimensions. And because of this, paying attention to computational complexity of algorithms in linear algebra becomes important. The notions of orthogonal or orthonormal basis can be naturally extended from the whole Euclidean or Hermitian space to its subspace. Proposition. Let U1 through US be an orthonormal basis of a subspace U in a Euclidean or Hermitian space V. Then orthogonal projection of a vector V in V to subspace U is given by the following formulas. So that projection of V to U is equal to C1 U1 plus CS US with coefficients CK given by the same formula. So this will be the scalar product of UK with V, where K now runs from 1 to S. And part 2, so if a basis W1 through WS is an orthogonal but not normalized basis of U, then the projection of V to U is given by C1 W1 plus CS WS, where the coefficients CK are scalar products of WK with V over the scalar product of WK with itself. To prove this proposition, let us recall how do we define the orthogonal projection. So the orthogonal projection of a vector V to subspace U is a vector in U such that the difference V minus the projection belongs to U perp. Because the projection is in U, so this means that we can expand this projection vector as a linear combination of the basis vectors of U. And the condition that the difference is in U perp, so this means that for all K, we must have the scalar product of UK with V minus C1 U1 minus CS US. This must be equal to 0. Now, to determine the unknown coefficients CKs from here, we just expand this expression. So then we get UK with V minus C1 UK with U1 minus CK UK with UK minus CS UK with US. So this is equal to 0. But now the basis of UJs is orthonormal. So this means that this is equal to 0. This is equal to 0. So all the terms are equal to 0 except for the kth term. So and here this scalar product is equal to 1. And then we obtain immediately from here that CK is equal to the desired scalar product UK with V. And this gives us the formula for the orthogonal projection of V to the subspace U. The second part of this proposition for an orthogonal basis I leave to you as an exercise. We make the following remark: that the expression that we use here. So this V minus the projection of V to the subspace U, which is by this proposition is given as V minus U1 with V times U1 minus US with V times US. So this is nothing but the orthogonal projection of V to the subspace U perp. And so this follows from the fact that we saw that this vector does belong to U perp. So this is how we calculated this vector. And from the decomposition that we proved last time, so that V is U plus U perp, so it follows that any vector V may be written as the orthogonal projection of V to subspace U plus the orthogonal projection of V to the subspace U perp. And then the difference of V minus projection to U is the orthogonal projection to U perp. And we also point out that if we take the orthogonal complement to U perp, then this will give us the space U. Now we come to the question, how can we construct orthogonal bases of subspaces? This is done with the Gram-Schmidt orthogonalization procedure. The idea is that we will start with an arbitrary basis, which is not necessarily orthogonal, and then apply this procedure to obtain an orthogonal or an orthonormal basis of the same space. Gram-Schmidt orthogonalization. Let V1 through Vs be a basis, not necessarily orthogonal, in a subspace U in a Euclidean or a Hermitian space V. We define a chain of subspaces. U1 sits inside U2, sits inside US, which is U, where the subspace UK is defined as a span of the first k basis vectors, V1 through Vk. So what we have is that for all k, the dimension of the subspace UK is equal to k. And so this chain of subspaces is sometimes called a flag. The idea of Gram-Schmidt orthogonalization is construct inductively orthogonal bases W1 through Wk of spaces UK. So that is, so first we construct the basis of U1, then we complete it to an orthogonal basis of U2, then we complete that to an orthogonal basis of U3, and so on. So the basis of induction is we take W1 to be just V1. But then for the inductive step, is that the basis vector wk plus 1, so this will be in the space uk plus 1. This is defined as vk plus 1 minus the orthogonal projection of vk plus 1 to the subspace uk. And the point is that by our inductive procedure, we have already constructed an orthogonal basis of the subspace uk. And so this projection is very easy to compute. Now let us write down the explicit formulas. So the first basis vector w1 is just equal to v1. Then the second one, w2, so this is equal to v2 minus the projection of v2 to the subspace u1. And w1 is a basis vector in u1. So this is v2 minus, so this projection by our formulas is w1 with v2 over w1 with w1 times w1. And now we get an orthogonal basis for the subspace u2 that consists of w1 and w2. Then w3 is v3 minus the orthogonal projection of v3 to the subspace u2. And here the basis is now w1, w2. So this becomes v3 minus w1 with v3 over w1 with w1 times w1 minus w2 with v3 over w2 with w2 times w2. And so on. So we continue this procedure. And so wk plus 1 will be vk plus 1 minus the projection of vk plus 1 to the subspace uk. And so this becomes vk plus 1 minus w1 with vk plus 1 over w1 with w1 times w1 minus minus wk with vk plus 1 over wk with wk times wk. We make a claim that for all k from 1 to s, the set w1 through wk is an orthogonal basis of the subspace uk. Here there are two parts to our claim. So first we say that w1 through wk is a basis of uk. And the second part of the claim is that this set w1 through wk is orthogonal. We prove both parts by induction. So for the basis of induction, so we set w1 to be v1. So there is nothing to prove. So we know that v1 was a basis of u1, and any set of one non-zero vector is orthogonal. Let us carry out the step of induction. We assume that first the span of w1 through wk is equal to the subspace uk, which is also the span of V1 through Vk, and secondly, that the set W1 through Wk is an orthogonal set. So this means that all of these vectors are orthogonal to each other. And our goal is to establish the same claims for k plus 1. Let us analyze the relationship between Vk plus 1 and Wk plus 1. Here we said that Wk plus 1 is Vk plus 1 minus the projection of Vk plus 1 to the subspace Uk. So this means that this projection lives in the subspace Uk, which is the span from V1 to Vk. And this tells us that this will belong to the span of vectors V1 through Vk and also Vk plus 1. Right? So because we have the term Vk plus 1 plus a tail that's in Uk. But we can rewrite this, and we can write that Vk plus 1 is equal to Wk plus 1 plus the projection to Uk of Vk plus 1. And again, this projection lives in Uk, but by inductive assumption, Uk is the span of W vectors from W1 to Wk. And this tells us that vector Vk plus 1 belongs to the span of vectors W1, Wk, and Wk plus 1. And this establishes the equality of these two sets, that now the span of vectors W1 through Wk plus 1 is equal to the span of vectors V1 through Vk plus 1, because each vector from one set belongs to the span of the other and vice versa. We conclude that the subspace Uk plus 1 is the span of vectors W1 through Wk plus 1, but this space has dimension k plus 1. And if k plus 1 vectors span a k plus 1 dimensional space, this implies that this set is linearly independent, and thus forms a basis of the subspace Uk plus 1. To prove the second claim, that vectors W1 through Wk plus 1 are orthogonal to each other, we observe that Wk plus 1 was defined as Vk plus 1 minus the projection of Vk plus 1 to the subspace Uk. But this is nothing else but the projection of Vk plus 1 to the subspace Uk perp. This implies that Wk plus 1 belongs to the orthogonal complement of Uk, and since all vectors W1 through Wk belong to Uk, this implies that Wk plus 1 is orthogonal to vectors W1 through Wk. And we conclude that all vectors W1 through Wk are orthogonal to each other. This proves that the Gram-Schmidt procedure, as we described it, creates an orthogonal basis of our subspace. Let us look again at what we have done. So we started with an arbitrary basis of a subspace U, and by doing this procedure, we constructed an orthogonal basis of the same subspace. And often we need an orthonormal basis. So how do we create an orthonormal basis? Once we obtain the orthogonal basis, then we just normalize every vector. So we create the vector u1, which is 1 over the length of w1 times w1. Then u2 is 1 over the length of w2 times w2, and so on. And then we get that vectors u1 through us will form an orthonormal basis of u. When we work with the Hermitian scalar product, the order of factors in the scalar product matters. So how can we remember whether we should put v3 as a first factor in this formula or as a second factor? So here the point is that the right-hand side must be an expression which is linear in v3. And the Hermitian scalar product is linear in the second argument. And because of this, the vector v3 should appear in the second components of the Hermitian scalar product in the right-hand side. In our description of the Gram-Schmidt procedure, we first construct an orthogonal basis of the desired subspace, and then create an orthonormal basis by normalizing all basis vectors at the end. There is an alternative approach where we normalize vectors as we go. So, for example, when we set that w1 is equal to v1, we can immediately compute the vector u1, which is 1 over the norm of w1 times w1. And then when we compute the vector w2, which is v2 minus the projection of v2 to the subspace u1, then this projection may be computed using the normalized vector u1 instead of vector w1. And because the length of u1 is equal to 1, this becomes simply v2 minus the scalar product of u1 with v2 times u1. And here we don't need the denominator because already u1 with u1 is equal to 1. And once we compute the vector w2, we immediately normalize it. So we say u2 is 1 over the length of w2 times w2. And then we proceed to computing w3, which is v3 minus the projection of v3 to the subspace u2, and we compute this projection using the orthonormal basis u1, u2. So this becomes v3 minus u1 with v3 times u1 minus u2 with v3 times u2. And once we get w3, we calculate u3 as 1 over the norm of w3 times w3. We see that in this alternative approach, the formulas are simpler because we don't need to carry the denominators. The drawback of the second approach is that when we normalize vectors, we often get square roots in denominators. So when we do calculations by hand, I find that the first approach is easier computationally. But if we are implementing the Gram-Schmidt orthogonalization in a computer program, then I would use the second approach, because for a computer it doesn't matter whether it operates with rational numbers or performing floating point arithmetic. Let us do an example. Find an orthonormal basis of a subspace U spanned by the following vectors: V1, which is the vector 1, 1, 1, 1, V2, which is the vector 2, 4, 6, 8, and V3, which is a vector 6, 6, 4, 0. Here we begin by saying that the vector W1 is just the vector V1, and then the vector W2 is V2 minus the dot product of W1 with V2 over the dot product of W1 times W1 times W1. So what do we have here? So we get V2 minus the dot product of W1, which is V1, with V2. So this will be 2 plus 4 plus 6 plus 8. So this is 20. And we divide by the dot product of V1 with itself, so which is 4. So times W1. And so we get the vector 2, 4, 6, 8 minus 5 times the vector 1, 1, 1, 1. And this will give us the vector 2 minus 5, that's negative 3, 4 minus 5, that's negative 1, 6 minus 5, that's 1, and 8 minus 5, that's 3. So this is the vector W2. And we see already that the vector W2 is orthogonal to vector V1 because the dot product of these two vectors is clearly equal to 0. Then we calculate W3. So that is V3 minus the dot product of W1 with V3 over the dot product of W1 with itself times W1 minus the dot product of W2 with V3 over W2 with W2 times W2. So that is the vector V3 minus the dot product of W1, which is V1, with V3. So here we have 6 plus 6 plus 4. So this is 12 plus 4, that's 16. And W1 with W1, that's 4 times W1. Minus, we take the dot product of W2 with V3. So here we get minus 18 minus 6. So that's negative 24 plus 4 and plus 0. So negative 24 plus 4, that's negative 20. And W2 with W2, so here is W2, we take the sum of squares. So minus 3 squared plus minus 1 squared plus 1 squared plus 3 squared. So this is 20 times W2. And then we get the vector V3, which is 6, 6, 4, 0, minus 4 times W1, which is 4 times the vector 1, 1, 1, 1. And so here we get plus the vector W2, which is minus 3, minus 1, 1, 3. And the result is 6 minus 4 minus 3, that's negative 1. 6 minus 4 minus 1, this is 1. 4 minus 4 plus 1, that's 1. And 0 minus 4 plus 3, this is negative 1. So this is the vector W3. At this point, we got the orthogonal basis of this subspace. And we can check that the dot products between W1, W2, and W3 are all zeros. And finally, to get an orthonormal basis, we just normalize. So the vector U1 will be 1 over the length of W1 times W1. So the length of this vector is the square root of 1 squared plus 1 squared plus 1 squared plus 1 squared. So they get 1/2 times the vector 1, 1, 1, 1. Then U2 is 1 over the length of W2 times W2. And here the length of W2 is the square root of the sum of these squares. And here we get 1 over square root of 20 times the vector W2 minus 3 minus 1, 1, 3. And the vector U3 is 1 over the length of W3 times W3. And the length of this vector is the square root of 4. So we get 1/2 times the vector minus 1, 1, 1, minus 1. And so these three vectors form an orthonormal basis of U. So this set of these three vectors. In conclusion, let us state several results related to orthogonal bases. Lemma: let W1 through Ws be an orthogonal set of non-zero vectors. Then this set is linearly independent. So in other words, so if we can verify that the given set of vectors is orthogonal, so this means that all vectors in the set are orthogonal to each other, then we don't need to verify linear independence. It will follow automatically. Proof: consider a linear combination of these vectors, which is equal to a zero vector, as we usually do when we prove linear independence. C1 W1 plus CS WS is equal to 0. And here we will be using the scalar product. So now we take scalar product with one of the vectors WK. So what we're going to get? So we get that 0 is the Hermitian scalar product of WK with 0. And then for the 0, we put this linear combination. So we have WK with C1 W1 plus CK WK plus CS WS. And then we expand this. And because the Hermitian scalar product is linear in the second argument, we get C1 times WK with W1 plus CK times WK with WK plus CS WK with WS. But because our set is orthogonal, we get that all these scalar products, except for the kth scalar product, are equal to 0. And then this will give us ck times wk with wk. And this is equal to 0. But our vector wk is a non-zero vector because we are given that all of these vectors are non-zero. And this implies that the Hermitian scalar product of wk with itself is also not zero. And then we conclude that the coefficient ck must be 0. And this is true for all k from 1 to s, because we can take arbitrary vector wk here. And so now we prove that all coefficients in this linear combination are equal to 0. And this implies that the set w1 through ws is linearly independent. The next proposition states that any orthonormal set u1 through us in a Euclidean or a Hermitian space V may be extended to an orthonormal basis of V. U1 through US through US plus 1 UN. And the proof of this statement is very easy. So we know that we can complete this set of vectors u1 through us to a basis, some basis of V, right? And we know because this set is orthonormal, it is automatically linearly independent by the previous lemma. And then we take this completed set and we apply to this set u1 through us vs plus 1 through vn. So we take this set and apply the Gram-Schmidt procedure. And if we apply to this set the Gram-Schmidt procedure, then we will obtain an orthonormal basis of V that will have as its first S vectors U1 through US. And one more proposition. Every subspace U in a Euclidean or respectively Hermitian space V is itself Euclidean or respectively Hermitian. Let us give a proof. So we construct using Gram-Schmidt procedure an orthonormal basis U1 through US of the subspace U. let V and W be two vectors in this subspace. Consider their coordinates with respect to the chosen basis, U1 through US. So we write V as A1 times U1 plus A2 times U2 plus AS times US, and W as B1 times U1 plus dot 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 plus BS times US, where AK and BK are complex numbers, or in F, right? So this is depending on the context, either complex numbers or real numbers. And now let us compute the scalar product between V and W. So this will be the scalar product between A1 U1 plus AS US and B1 U1 plus BS US. This will be the sum over K from 1 to S and the sum for P from 1 to S. And here, when we pull out A coefficients from the Hermitian product, because in the first term we need to take complex conjugation, so we get AK bar times in the second term we have linearity, so here we're going to get BP times the scalar product of UK with UP. But this basis is orthonormal, so we get that the scalar product of UK with UP is going to be 1 if K is equal to P, and 0 if K is different from P. And so then we see that in this sum, we only take terms where K is equal to P. So this becomes the sum. K goes from 1 to S. And here we have AK bar, and P must be equal to K times BK. And what we see is that this is just the expression for Hermitian scalar product, or for the dot product, if this happens in a Euclidean space. So our conclusion that with the scalar product inherited from V, U is isomorphic to RS, so in Euclidean case, or U is isomorphic to CS with the standard Hermitian product in the Hermitian case. By choosing an orthonormal basis in the subspace U, we obtain that the scalar product inherited from V assumes the standard form. This becomes the standard scalar product either on RS or on CS. We point out that this result does not hold for the complex space Cn with a bilinear dot product. So if instead of the Hermitian scalar product, we take a bilinear dot product on Cn. And here, as an example, let's take U to be a one-dimensional subspace spanned by the vector 1i, and U is a subspace inside C2, then what we have seen is that the standard dot product on C2 restricted to U will become 0, because the dot product of 1i with 1i is equal to 0. And as a consequence of this is that U is not isomorphic to C1 with dot product. In Cn, we can construct subspaces such that the dot product on Cn restricts to a 0 product on these subspaces. Such subspaces are called isotropic.